So the next presentation is spectro-electrochemical characterization of ultra-thin film of PDHD single crystal electrode and gold on PD nanoparticles by Professor Tian and Xiamen University, and also the co-chair of the conference.
Thank you, Peter. And I would like to begin by thanking my co-workers, especially Professor Jianfeng Li. And most of the people here are from his group because he is my former PhD student. So when I have some idea, I just ask for his help. And as you can see that on the title, I modify a little bit because during these 3 days lecturing and discussion, I really just learned a lot from those excellent talk and very active discussion. So that I would like to start just showing one slide that I do not change a single word. That was presented 5 years ago in the satellite symposium of ICCF-23 in Xiamen. And in that time, I asked myself, what is the key issues or key factors for this cold-fusion field? And it can be divided into sample preparation, including loading, triggering, and characterization and theories. However, it's quite complicated because there are so many unknown issues or complicated issues, including those sample preparation and characterization methods. So I fully agree with Michael McClure on that reproducibility is truly important because I have been engaged in this field since 1989. In fact, I spent half year in the Institute of Cold Fusion in Utah and Salt Lake City together with Martin and Stan. So that I just follow up some study, but not comprehensively. After listening to many lectures and discussion, I just put more issues, not less, but more issues on this table. And I think it's possibly the time to discuss how to identify the best experimental or protocol and how to utilize the advanced technique to carry out more systematic studies and in order to explore some new issues and to solve some unknown problem. And of course, I can give you more detailed explanation on this table, but as you can see that we really wanted to figure out what is the most important part. And I think if we want to have get some positive results, we have to triggering in general. And we have to first prepare a good sample. Then we can have more opportunity to trigger and detect some useful signal. So that it's important that we have here some good lectures about this, but I'm wondering how to provide a protocol or samples that can be reproduced by other groups. And of course, this is for basic research. And so I think we need to clarify and two levels. One is on basic research, so people can easily share their idea and their thought. If we go to the industrial level, I know it's so difficult. So here, what I'm talking about are all on the base of fundamental research. So that I think the condensed matter or materials or lattice could be quite unique and very different from the exist picture if we want to get a cofusion in general. And so the lattice assisted nuclear reaction should be initiated by several non-traditional ways. Here I just point out two ways. One is to trick material or lattice, and that we need to make this material or condensed matter or lattice dramatically different from its static state, from its conventional structure, because we possibly need to have some channel to bring the nuclear closer, as close as possible. But there could be another way if we could design and construct rationally on some stable but very unique structure that may form or attract nuclear pair or nuclear class very close to each other. But this is kind of similar to the tracker of the field of semiconductor, because in general, people don't think two electrons can attract each other to form pair instead of a repulse from each other. But the nuclear, of course, is much, much more difficult than electron. But I'm not quite sure if it's possible. So that what I mean that we need to trigger this active size for the nuclear reaction, which means if we stay at room temperature and with a conventional or ordinary lattice, there will be no chance to do so unless we have semiconductors-like materials. So, but if we want to trick this and change it from different level, and it's very, very hard, because the trick is try to create some active size, and then that we can detect. So how to prepare material, I think, is a crucial issue, and how to trick it is also very, very important. And nowadays, I'm still think that it's too rationally create a good active size, that can easily reproduce, and that we can easily detect those active sites, because it must be quite few. You cannot have a very huge number of active sites. At the present stage, I don't think it's so easy. So we are facing so many unknown phenomena and out of control factors for very complicated system under ill-defined or an ill-controlled system, even we are facing some runaway condition. So, and this is extremely challenging. And as we can say that life science, our body, for example, is also kind of a condensed matter. But it's happened. There are so many bio and chemical reactions. But here we want to have a nuclear reaction. So it's totally different. So it's more challenging. So especially nowadays, we still lack of solid and theories at this moment to support, and we still lack of very powerful and capable of creating active sites and detecting active sites. So, in my opinion, that there are two approaches. One is just have a relatively easy sample and prepared and have a good trigger process, or we have some structurally well-defined. Then we can create something that possibly is relatively under control. Then we make a triggering. So we possibly need to simplify either this part or this trigger part. And if we have too complicated mixed together, then this constant would be very, very high. But we need to have a small constant, and so it's to reduce one of complexity if possible. And this slide I have shown in the opening ceremony. What I would like to emphasize at this moment is that, in fact, if we go follow up the long development of surface science, and it's really go to this direction. And we now have a very structurally well-defined surface, and people can create structurally clear, including single item catalyst nowadays. So of course, this is still far away, but I think this give us some confidence or hope that we really have a chance to do so. So regarding the well-defined system, I think a nanostructure could be one of a possible way, because it can provide more active size for more or possible nuclear reaction, and it could be easier to regenerate, because I always wonder if we cannot go back to the original one, then the reproducibility seems to be quite complicated and quite challenging. So that because the lattice after triggering will be significantly distorted or had some phase transition or even cracking. So that it's a kind of a important thing is that if we can regenerate easily, and we can provide this kind of a protocol to the people, so that the people can repeat it and make this kind of a sample. Of course, it's also a challenge. However, you can see, for example, the palladium nanocrystal can be formed by different way by utilizing chemical synthesis. And there can have a shape control as well, and they even can have a bimetallic dendrite from simple to complicated system. So the nanoscience has been developed quite fast, and so we possibly can have a more chance to get to know some nanocrystal or nanoparticle that are useful for our study. So that these are just some example. Now let me just go to my abstract, because we think another branch of a nanostructure is not three-dimensional nanoparticle, but thin film, ultra thin film, with a maybe few monolayer, from 1 to few monolayer or to few 10 monolayer. And it can be prepared by several ways, especially by atomic layer deposition. And there is a small branch of ALD using electrochemical deposition way. For example, this is a gold 111 surface, so we can utilize under potential deposition of copper. to just get one monolayer of copper. Then we can play chemical reaction, redox replacement. So the palladium, we can add some palladium ion. So it can replace copper with palladium. Then we can go into the electrochemical way to have a second layer, UPD. Then redox replace one layer by one layer. So it's very, very well controlled. And so that we can get one more layer of palladium. The reason I want to get one more layer, in fact, and I just want to see what is the hydrogen location, because we all know that hydrogen can be observed by palladium. However, it cannot go into the gold material, gold crystal. So that the hydrogen has to stay somewhere. And that's some kind of an idea I really want to solve out. So I've been working with Jianfeng Li for many years. And as you can see here, that we utilize electrochemical cyclovoltammogram of hydrogen. You can see this is the first layer of palladium. And then we have the third layer here, then 5 molar layer here. So as you can see, it's just increase the thickness and increase the potential deposition of hydrogen. Please notice that the hydrogen evolution will take place here, so that the current will be huge here. However, here we can carefully design and carefully and design some hydrogen or deuterium adsorption and absorption. We also can calculate to find out that the adsorption step is the rate control step instead of absorption, because absorption is huge. And so that we take this up and sample and ask another co-worker, Professor Sai Duan, to simulate this system and to see what is the location of hydrogen. And as you can see, it's very quite interesting. For the one molar layer, the hydrogen is still, it's not on the top side, but it's still in the hollow side. And so that we try to find out the spectroscopic method and evidence is still very difficult, because hydrogen is so small. So once they just go into the hollow or bridge size, and spectral just lost the signal. And you can see, if we put a 3 layer of palladium, then we can get a kind of hydrogen adsorption. We cut off from this 3 layer to 1 molar layer. You can see the molar layer close to gold 111, and those are bright spot that is belong to hydrogen. However, if you change it to 5 molar layer, the situation has been quite interesting. As you can see, the first layer, hydrogen is up. The second layer, hydrogen is down. So the hydrogen on these 2 layers is quite close. But for the first layer and the second top layer, hydrogen is separate. So that is provide some interesting modeling that so we want to detect and to see if it's possible to get the signal from this type of hydrogen palladium or even phonons for this thin layer, because we cannot get any phonon signal of Raman spectroscopy from the bulk palladium. And unfortunately, that we fail so far to get the signal either of hydrogen, palladium, or the phonon of lithium film. So we change idea. So we just overcoat the ultra thin palladium shell on the gold nanoparticle, because the signal is much stronger. So that, as you can see, we can perform the spectro-electrochemical measurement and to see this gold nanoparticle coated with palladium. Then we can see those low frequency band, which we never observed before. So it's quite interesting. And it's getting relatively stronger when the potential is close to the under potential deposition of hydrogen. And we change the cation to see if there is any effect, but no any effect on those things. And then we get we check, we utilize the bare gold nanoparticle, no signal at all. Then we just go to the deuterium, and it's surprising that this band does not change. They only change with potential, especially on the threshold of the potential deposition of deuterium or hydrogen. Then we asked Professor Pan Feng to just carry out very, very preliminary, because we asked him 2 days ago. So he just provided very briefly result and give us some trend that with hydrogen or deuterium, this peak possibly can shift a little bit. So that, and as you can see, we also check the thickness dependent. And the situation is quite similar, no considerably difference. But of course, as I mentioned, these are all very preliminary studies, and of course, our students have been careful to recheck to do this experiment by several rounds in order to be sure that these peaks are real. But the assignment, I must say, we have not yet confirmed. And as you can see, we change the phases of GO111 to GO110, and we can also see dramatically change of electrochemical behavior in the potential deposition. So I think my time is up, so that I would like to just give this a very the slides. I thought it could be important for the discussion in the next hour. And I am a little bit confident because the 2 months ago, this is science just announced this 125 questions, and will co-fusion ever be possible is one of them. So I'm a little bit optimistic that we possibly can get more people and more projects and more money to this field in the near future. So with that, I would like to thank my co-workers and also those co-workers who have been working with me in the past 12 years. We got one project from NSFC 8 years ago, and that was the last one we get. Now we just can do not have any grant at this moment. So thank you so much, and I will be pleased to answer your question in the discussion session because I'm running out of time. And thank you for your attention.